So last time we reached this interesting discussion, but now we actually have to go about the work of calculating, again, what's my change in entropy from my stretch system, so my really stretched out system, to my spaghetti system. So again, we could use Boltzmann expression. We know that it's just going to be the ratio essentially of, my change in entropy is just going to be the ratio of my number of microstates in the stretched versus the unstretched system. So we have this expression, and actually you can go back through some old NEC 202 notes to kind of look at that expression. But this is our number of microstates in essentially our relaxed form, so our spaghetti form, versus you can kind of see this is just this R naught. This R naught is essentially our relaxed condition. So there's 1, 2, and 3 coordinates. You can think of it as like X, Y, Z, again, whichever. And here we know that alpha is, remember, alpha 1 is equal to L1 divided by L naught. So essentially, and then our L naught, again, you could just assume this is like 1. So this could be simply L1 over 1. So this is our alpha, which is our kind of extension ratio. So that's what we're kind of looking at here. So we have this in terms of what is the new coordinate system. So this is our new coordinate system here. And again, we know that they look Gaussian because, again, why? Why does this, have this kind of Gaussian shape? Because we assumed, again, basically on our relaxed and stress dimensions above, but also we assumed, again, that Gaussian distribution between our subchains. So we could go through all of the fun math associated with it, and then we get to this expression. But you see here that we're left with these kind of relaxed coordinate systems, right? These 1, 2, and 3. And I could relate my relaxed coordinate systems to my R naught squared here. So I can plug this value in, rewrite my expression, and especially since I know that R naught is just NL squared, so these are going to cancel in here, and I'm left with this very simplified expression in terms of my my alpha, my extension ratios, and then I can now finally start to calculate what is my force in each of the directions as a function of this change in S as a function of my extension ratios over the lengths. So next time we're going to look at uniaxial deformation of a rotor network and find a really, really cool expression for Young's modulus. So see you in the next video. Thanks.